We have discussed the classification of the wave shaping circuits. Wave shaping circuits are classified into two types: linear wave shaping circuits and non-linear wave shaping circuits. In the linear wave shaping circuits, we use only resistor or capacitor or inductor. We have RL circuits and RC circuits. But now we are discussing about RC circuits, RC differentiator, and in later class we will discuss about the RC integrator. The same thing can be implemented by using the RL circuits also. Because these three elements are linear and passive: resistor, capacitor and inductor. So these wave shaping circuits are called as linear wave shaping circuits. The topic name is differentiator. Differentiator means the same differentiation we have learned in the mathematics as absolutely. But here we are doing the differentiation for the signal. In the mathematics you might have learned differentiation of cos x is minus sin x, and differentiation of sin x is cos x, and the differentiation of t square is nothing but 2t. This is the differentiation we have learned. This differentiation now we are performing for an electrical signal. Any physical signal in the universe can be converted to the electrical signal. So whatever the physical signal you want to differentiate, if you convert that to electrical signal, my circuit is capable of differentiating that signal. Here we are using a simple capacitor and resistor. This two element circuit is capable of differentiating my electric signal. This is called as high pass filter. The high pass filter frequency response I am drawing here. This is the frequency response of the high pass filter I have taken. Example, this is the cutoff frequency, and on x-axis I am taking frequency, on y-axis I am taking gain. After a particular frequency f, that is what we are calling as the cutoff frequency, this circuit will allow the input signal as it is, because we are saying the gain is 1, output by input if we are taking. Before the cutoff frequency, if we are sending the signal, then the circuit is attenuating that signal. We are not getting whatever the amplitude we have given as an input. So here, this is acting like a high pass filter, because after a certain cutoff frequency, the signals are passing through this circuit, but before that the signals are being attenuated by using this circuit. I am taking V in and V out I am taking at the resistor. This high pass filter, I am saying, after a particular frequency it is not allowing, before the particular frequency it is not allowing the signal. After the particular frequency only it is allowing the signal. That's why we are calling it as a high pass filter. That concept we are trying to explain with the capacitive reactance. This is capacitor and this is resistor. The capacitive reactance Xc is equal to 1 by 2 pi Fc. When the F is very low, if you take 0, then the capacitive reactance is very high. When when we are taking the high frequency signal, means F is equal to infinity if you take, then Xc is very low, or Xc is becoming 0. So for the high frequency signals, this capacitor is acting like a short circuit, a simple wire, and for the low frequency signal, this capacitor is acting like a open circuit. It is blocking that. That is the property of the capacitive reactance. But now we want this circuit to be operated as a differentiator. There is no doubt this circuit is a high pass filter, but when this high pass filter will differentiate my input signal, for that we are saying a particular condition for performing the differentiation is the RC we are taking, the time constant of the signal we are taking, the input signal is having some time period. So this signal is having the time period which I am representing with the t seconds, and my circuit is also having time constant. I am representing that also with RC seconds. my circuit time constant should be very much lower than the input time period. At that condition, my input signal will be differentiated. So what is the condition? If my circuit time constant is very much less than the input time period, then the circuit will differentiate the signal. That's why generally we take capacitive reactance very much higher than the resistor. Generally 10R. I am saying capacitive reactance. I am not saying about the capacitance value. Capacitive reactance we are taking generally 10 times larger than the resistance value. We will try to design a small simple circuit. A person is sending a 1 kHz signal. Maybe that is a square wave. So this is a square wave. He wants this signal to be differentiated. It is very difficult to us on paper to differentiate signal. We are taking the capacitor and resistor, then this is capable of differentiating the signal. But the problem is, we have to design these values R and C. Now he is asking, what R and C values I have to take? Then we will design those RC values. We are taking the frequency as 1 kHz. The time period will be 1 millisecond. As the time period is 1 millisecond, the R and C values we should take in such a way that R into C must be less than the 10 to the power minus 3. I am taking the resistance value 1 kilo ohm and I am taking the capacitance value example 1 nanofarad. Definitely this will be very much less than 10 to the power minus 3. The 1 kilo ohm resistor and 1 nanofarad capacitor, this circuit is capable of differentiating the input square wave with the frequency 1 kHz. So we have designed, but we have to rely on the mathematical conceptualization that this circuit is capable of differentiating the signal. So we have to derive this by using a mathematical derivation. For that we are taking V in is equal to the voltage across the capacitor plus voltage across the resistor. The voltage across the capacitor we know 1 by C integral of I dt when the current in this circuit is I. And the voltage across the resistor is I into R. But because I am repetitively saying that RC, the time constant of the circuit, is very much less than the time period of the signal, we are having a very small time constant. Practically, we will try to understand what this time constant, small time constant is doing to our circuit. When we are having a small time constant, this capacitor charges very fastly. Means within that time only the capacitor is charging. Now we have taken the time constant 10 to the power minus 9 into 10 to the power 3, 10 to the power minus 6, 1 microsecond. This capacitor is charging within that fraction of time, in 1 microsecond. So here we are taking one basic signal, maybe this as a step signal. Step signal we will represent mathematically. U of t is equal to 1 when t greater than or equal to 0 and it is 0 when t less than 0. This signal, if I want to differentiate, if I am having a very low time constant, I will get the output like this. I am taking a rectangular pulse. Example, this is the rectangular pulse. If my time constant is very much higher, I will get the output like this. If still I am decreasing the time constant, my output will be like this. I am still decreasing, my output will be like this. When my time constant is very much low, the output will be like this. This is signal we are targeting. This is what we are saying as a differentiated signal. Because suddenly here, the voltage is changing, the capacitor does not allow sudden changes. Immediately, we are observing another spike here. This is the differentiated signal which we get from the rectangular pulse. Similarly, when we give the square wave, the output will be, if I am taking a very low time constant, then output will be a series of spikes. It is very difficult to generate these spikes by using the function generator. but it is very easy to us to differentiate the square wave because the function generator we can easily generate the square wave. By using the square wave and simple RC, resistor and capacitor on our breadboard, we can generate this signal, this spike signal. That's why in the need of wave shaping circuits we have discussed complex signals can be generated by using the simple waveforms we have. It is very easy to get these square wave. From this square wave, we are generating this complex signal. This is called as a differentiated signal. Sir, why you are taking square wave? Why can't we take the sinusoidal signals, sir? Linear wave shaping circuits, when we give the sinusoidal signals as input, it is very difficult to understand the circuit function because we will get the output also sinusoidal signal only. When we are giving the input sinusoidal signal, output also we are getting the sinusoidal signal. That's why we are not able to understand the function of the circuit. That's why we are giving the non-sinusoidal signal, square wave. When we will learn about the non-linear wave shaping circuits, mainly clippers and clampers, at that time we will give the sinusoidal signals because those circuits are capable of changing the output shape even if we give the sinusoidal signals. Now mathematically we want to derive this one. When we are having the low time constant, the entire voltage will be dropped across the capacitor because within less amount of time the capacitor is charging. The voltage across the resistor is negligible, we can neglect it. So here V in is equal to 1 by C IDT. But I want the relationship between the input and output. For my convenience I am writing V0 is equal to IR, therefore I is equal to V0 by R. So here we are taking V in is equal to 1 by C V0 by R dt. So this will be V in is equal to 1 by RC V0 dt. When we are differentiating both sides, dV in by dt is equal to 1 by RC V0. Therefore, V0 is equal to RC into dV in by dt. So, output is nothing but it is a function of derivative of the input. V0 is directly proportional to derivative of the input signal. That's why this circuit is called as a differentiator. For differentiating the signal, we are taking the two elements, two passive elements, linear elements, resistor and capacitor. This signal, the input signal time period should be higher than the RC time constant, then the signal will be differentiated. This is the differentiated output when we are giving the square wave signal. If the amplitude peak to peak is V here, then this is V and this is V. Peak to peak amplitude we will get here. V and this is V. This is how we will differentiate the signal by using a simple RC circuit.